Different receptor classes dominate the two modes of neural firing, namely tonic and phasic firing patterns. We would expect the receptors that lead to tonic or phasic spiking to be associated with neural excitation because spiking occurs when a neuron is excited. Since the main excitatory neurotransmitter is glutamate, we would expect the receptors underlying tonic or bursty firing patterns to take glutamate as their driving input. Indeed, that is the case. In the case of ionotropic glutamate receptors, tonic firing is primarily subserved by AMPA receptors that, in the aggregate, allow ions to pass through their pore to the degree that glutamate binds to them. As such, the firing rate of an excitatory neuron can increase in an analog manner. The more glutamate released into a synapse, the faster the average firing rate of the neuron. NMDA receptors, in contrast, which are also glutamatergic receptors, subserve phasic firing or neuronal bursting. NMDA antagonists reduce bursting, that is, the frequency of pairs and triplets of spikes separated by only a handful of milliseconds decreases. Here's an animation showing how glutamate binds to AMPA receptors. The opening of AMPA receptors depolarizes the postsynaptic neuron as the net positive charge inside the postsynaptic neuron increases. NMDA receptors stay closed initially. In order for NMDA receptors to also open, it's necessary that three facts be true. Glutamate has to bind to the NMDA receptor. Another chemical called D-serine or glycine has to bind to it as well. And the postsynaptic neuron has to already be depolarized. This means that NMDA channels can only open if AMPA receptors have already allowed the postsynaptic neuron to depolarize. So, NMDA receptors are also coincidence detectors. Whereas neurons are coincidence detectors in the sense that they are waiting for the simultaneous arrival of presynaptic action potentials, NMDA receptors, which are orders of magnitude smaller than a neuron, are waiting for these three facts to all be true. If they're all true, a single atom, which happens to be a magnesium ion, which functions like a stopper in a drain, comes unstuck from the receptor pore. It just drifts off and the receptor becomes unplugged, so to speak. When an NMDA receptor opens, positively charged calcium ions enter the postsynaptic neuron. The sudden influx of calcium ions makes NMDA receptors very different from AMPA receptors because calcium ions cannot pass through AMPA receptors. This calcium massively depolarizes the postsynaptic neuron and triggers bursting, which can also be thought of as firing at an extremely fast rate, at least for a moment. Calcium, it turns out, is actually quite toxic for neurons, so it's typically contained in little compartments called dendritic spines. Here's a picture of a pyramidal cell with dendritic spines evident here. So if you see a neuron that has dendritic spines, you can infer that it is an excitatory neuron that takes glutamate as its key driving input neurotransmitter, and that it will have AMPA and NMDA receptors at the location of its spines. The main neurons that have spines are pyramidal cells and a kind of local cell that is a lot like a pyramidal cell called a spiny stellate cell, but which lacks the long axons of a pyramidal cell. In contrast, if you see a neuron that entirely lacks dendritic spines, you can infer that it's probably not an excitatory neuron that takes glutamate as its input. You can reasonably, though not perfectly, infer that a spineless neuron is an inhibitory interneuron. They have many different shapes, as shown here, but they all tend to be smooth and lacking in dendritic spines. They also tend to release GABA on downstream neurons, inhibiting them or hyperpolarizing them, making them less likely to fire. Because bursting turns out to be a central part of neural communication, it should not be a surprise that knocking out NMDA receptor function knocks out bursting and thereby knocks out normal neural information processing. In fact, many of the main classes of anesthetics, which knock out consciousness, operate by knocking out or antagonizing NMDA receptor function. Bursts are thought by some neuroscientists to propagate across an information processing network as units of information, as we shall soon see.